Okay, this is the continuous video for our module 6. Before we're going to go deeper, I'm going to do some recap for our previous subtopic under our module 6, which is on the basic adder. Last time in the basic adder, you already go through on the half adder and full adder, if you still remember. I hope that you remember because it's nearly to your test too. Okay, now without further delay, let's proceed to our basic adder. You need to have very strong fundamental in this basic adder before you can go for parallel binary adder and also a comparators, as well as all the others like decoder, encoder, multiplex, and all of this. Okay, let's move. These are arithmetics on the mathematics term, I think. So I hope that no need for me to repeat several times, because this one we already touched since like our module 1, I guess. So please make sure remember this. And in our basic adder, we're going to look into half adder and full adder. Okay, in our basic adder, if you still remember, I asked you to remember on the Boolean expression, especially for the sum and the carry. Oh, before that, on the half adder, you not only for the half adder, similar to also full adder, you need to know on the block diagram how it look like. How many input is have, how many output it's got here, right, on the half adder. And in the input side, what is available? Okay, here for half adder is only for the variable input. Next, on the output, you need to have sum, you need to have carry. That is why after that is come for you to remember on the Boolean expression. This one you need to remember. And this look it for your what block diagram. Let me check. Okay, I already record. This is only for your block diagram, but you need to also know how the circuit inside look like. Last time we already go through how basically it's look like. This is look like this one. You have your sum, you have your carry, which is both is your output, and this is your input. Inside of this, you're going to have X or exclusive or and also and get. And it is, you can see here, you need to remember also. If you can't remember, you need to understand the circuit inside and the function of the sum and carry, then you can come up with your truth table. This one is from your module 1 for the AND and for the XOR, exclusive OR. Okay, go through for our full adder. You can see the things, similar things that I remind all of you to look into in your half adder, which is you need to know how many inputs it have. So here there is 3 inputs, 2 variables, and another one is input carry. Then later on you will know, okay, what is the purpose of input carry there. And then for the output side, you have a sum and also a carry out. This is only the block diagram here, but in terms of circuit look, how it look like. Before we go for a circuit, we need to know on the truth table. Okay, so from the truth table, we can come out with our K-map to get the simplified version. Then last time we already derived all these equations, expressions. And finally, we got here for our sum and also our carries like this. carry out, not carry in. Okay, that's why lastly you get the circuits look like this for your full adder, and this is much better looks, I guess so. You can see it clearly. You have this half adder and another one is another half adder, and by using these two half adder you add using your OR gate here, you combine it together, it's come to full adder. And how are you going to connect half adder and half adder to be your full adder? It's going to be look like this. You have half adder, you have half adder, and then you combine them and add using your OR gate there. Then you will get your carry out, and the output for your half adder, you're going to get the sum. Okay, let's move on. Here is an example of the input and also the output. It's very easy. It is like your normal mathematical things you can see here. Let's we go directly to our here is example also. Okay, here is example, but it is in terms of adder or subtractor circuit. This circuit implement two's complement arithmetic, which is if s equal to 0, implement a plus b, no changes to b because b xos equal to b xo equal to b. So this is the xo characteristic that you already learned. Therefore, full adder will do a plus b. If s equal to 1, where is your s? So, if s equal to 1, implement a minus b. Minus b will be second complement of b because b xo1 equal to b bar, which is the first complement of b. To get, okay, you can read it by yourself. You can see here, this is a combination of your full adder, full adder, full adder, and these all circuit will combine together to be whether it can act as a adder and also subtractor depending on the value of your s here. If s here is 0, then this circuit will be read as a adder. And when s is equal to 0, it's going to read it to be as a subtractor. If you can go through here, you can read by one by one, then you can understand. Okay, note that full adder, FA is full adder, C is your carry, input is A and B, and output is your S there. Initial S will be given normally in the equation. Okay, so here is example for a parallel adder. You can see here when you have a combination of two full adder. Two or more full adder are connected to form a parallel adder. So this one will be your parallel adder. You can see here s equal to 0, which is your this part you can see, but it depends. Sometimes this one can be 1, and for this parallel adder it is a 0. It's going to be at general format additions of 2-bit number. You have here 2-bit, you can see, because you have one input to your full adder 1, and this is your full adder 2. So this one you're going to add together, you're going to have sum 1, sum 2, sum 3. This is your sum 1, this is your sum 2, and your carry out here will be sum 3. For carry out for FA1 will be the carry in for the next FA2. If let's say you were given with A equal to 1, 0 and B equal to 0, 1. So this one will be A0, this will be A1. This will be your B0, this will be your B1. So because of this, the question will inform you of whether this is A0 or this is A1. It's depend, okay? Sometimes might be the person in charge that who did the questions are doing vice versa. So you need to note on the value whether this one is A0, this one is A1, B equal to like 0, 1, B0, B1. It depends. So the question will inform you. As long as, but by default it's going to be followed like this, from 0 to the left, much higher numbers, right? Okay. Now you just put it here in your circuit there for parallel. Oh, but here you have only a 1 and 2. Okay, it's okay. We can change it. Okay. Now we have A1 is 0, B1 is 1, A2 is 1, B2 is 0. We have here 0. 0 plus 1 plus 0 is going to be 1 for the sum, and the carry will be 0. This is mathematics. I don't want to discuss it anymore because this one is an early of this page slide just now, and we already several time learning on this. Okay, you have here now at the second side you have 1, 0, 0. 1 plus 0 plus 0, you're going to get 1 for your sum and 0 for your carry, and your final answer will be 0, 1, 1. Okay, so you can try also several others value. Let's say 1, 1, 1, 1 for A and B. Let's take a look what will happen. 1 plus 1 plus 0, it will be 0 for the sum, 1 for the carry. Carry will be your carry in here. 1 plus 1 plus 1 will be your sum as 1, and your carry out will be 0. Your total output will be 1, 1, 1. Okay, it's very easy. Then here, okay, there is an example. Determine the sum generated by 3-bit parallel blah 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 blah. You were given with the value there are picking added. So here is your A, another one is your B, and you can draw your full adder there. Let me put the value in 1, 0, 1. Another one is 1, 1, 0. Let me add it all. C0. What is the value of C0? It's dimension here. 3 parallel below, added below, and shows the immediate carry when the binary are being added. Oh, C0 is not given, so I don't know what is the value, but we can assume, let's say it's going to be 0. We will have 1, 1, 0. It's going to be 0 for the sum, carry out will be 1, and carry in for the our FA2, FA1, and FA3. So 1 plus, okay, here will be 0, here will be 1, carry in 1, 0, here will be 0, here will be 1. So your final answer will be 1, 0, here only, okay? This is only your sum, 0, 0. So this is the answer. Okay. You can see it's connected to the ground there because it is an adder. So this is the final answer. The example in hard way, just now you just see in terms of the block diagram there. but in terms of circuit, when you have these MSI chips, you're going to use these chips and you combine all the connections like this, then you will get the adder example. Okay, so this one is a 4-bit parallel adder, basically similar whether it is 2 parallel adder, 3 parallel or 4, it's just similar. You need to know the carry in input carry, the carry out will be bring to the next carry in, carry out will be bring to the next carry in, and you answer only for the sum and the last carry out for the last full adder. Let's take a move. There you can see you have an example for your chips there. Our MSI chips for 74L S283. So you have several pin. You can see here, this is your pin 1, 2, 3, 4, which is this one 1, 2, 3, 4, and another pin for your input B, which is 1, 2, 3, 4. So another 4 pin there. So this is all the input for your adder, 4-bit parallel adder. And of course, you're going to have your C0 there, input carry. And your output, what is your output? Your output will be this, and lastly, this one is as carry out only. So you have 4 sum there, and another one is your carry out. Then you can show in terms of the arithmetic operation like this. Okay, two type of parallel adder based on how it handle a carry. You have ripple carry adder and also loop ahead carry adder. So you need to know what is the difference between each other. You can read. Okay, carry out of each full adder is connected to carry in the next order stage of the full adder, which is basically quite similar with our parallel adder. And carry accumulate from the lowest order bit to the highest order bit. Speed of additional limited by the time required the carry to propagate or ripple through all the stages. So this is very important to differentiate between your parallel adder and also your ripple carry adder. Circuit simpler than look ahead carry adder. While for your look ahead carry adder, speed up the addition process by eliminating ripple carry adder. So it is related to this and it's going to rip the carry delay. So please make sure you read these statements for another parallel adder, because this is all parallel adder, but a type of parallel adder, ripple carry adder, or also another one is look ahead carry adder. You need to know the differentiate between each other. Done with our adder. Now we move to another subtopic for our comparator. Comparator, here we can see compare to n bit, whether it is 2 bit, 3 bits, 4 bit, but you're going to compare between two. Let's say I compare my Samsung phone. I'm going to compare with Apple phone. So I'm going to compare between two. So you cannot like compare directly to 3. So that's why here you're going to compare 2, but on the bit is depend. Sometimes you're going to compare with 2 bits, 3 bits, and etc. Binary value to determine which one is larger. Like me myself, if let's say I want to compare about my phone, I'm going to compare. Let's say, okay, which one much more expensive? So that is the things in terms of comparison, right? And here you can see input to single bit input, whether X and Y, and the output is 3 line, whether it is more from between these two or equal or less. So that is the output. Output must have 3 line, whether more, equal or less. And normally we're going to use XNOR gate can be used as a basic comparator. Use XO to check the single bit inequality. So you can see this one whether it is equal or not for XO. But for XO, XNOR is equal, which is we want to compare, and XO for a single bit inequality. Okay, here there is example there. You have XO gate as a 2-bit comparator. You have here 0, 0. Satu bit je. This one is 1 bit. Tapi you going to compare with 2 input. Let's say you have input A and input B, 0 and 0. If you compare, then you can see you're going to get output as a 0. If 0 means that it's equal. And you can see here A and B. You want to compare 0 and 1. If you get 1, then it's not equal. You can compare between these two only because this one is a basic. Same goes to your XO here. This one is XO, right? You're going to compare only whether it is equal or not equal or not. If equal, it's going to be 0. If not equal, it's going to be 1. Not equal, you're going to get 1. Equal, you get 0. To check for n bit equality, which is your XNOR, combine the result of comparing n and single bit comparator. So you have here, you're going to compare this first. For your LSB, if you have like, let's say 1, 0 and 0, 1. This is B, this is A. This will be your A0, this will be your A1. This will be your B0, this will be your B1. So you're going to compare, let's say, we have here 0 and 1. Here will be your A1, 1 and 0. You can see it is not similar. Not similar, you will get 1, supposedly, right? But then you have not here, you're going to get like a 0 there. Here, also similar. Then you will get 0. 0 means that it is not equal, supposedly 1. Okay, this one is like maybe a comparator. You can assign it if 0 is going to be equal, if 1 is going to be not equal. So just now we are using only O. Now we're going to use XO. That's why it's different with this one. Just now XO 0 is equal. Of course, if you have not, it's going to be not equal. Okay. High indicate equality, whether it is equal or not equal. High indicate equality, A equal to B. But here you can see we got 0, means that it is not equal. Of course it's not equal, right? Okay, let's try. Maybe we have 1, 1, 1, 1. So it is equal. 1, 1, 1, 1. Here we will get, if 1, 1. XO, what happened? 1, 1 XO, we will get 0 here, and here will be 1. Similar to this part, 0, this one will be 1. 1 and 1 is going to get high. See? So it's going to be equal. How about if it is 0 and 0? Can it be? 0 and 0, we will get 0. Yes. 0 and 0, we will get 0 here. We will get 0 here. And our knot, we will get 1 and 1. Of course, we're going to get 1. Yeah, correct. Means that it is equal. So this is a comparator. Comparator, you need to know how from basic things using XO. You need to remember all these functions, but this is basically on your module 1 already, and you're going to compare whether it is equal or not for XO. Similar to XNO. XNO, of course, it is vice versa of your XO. Compare the equality for these 2-bit binary. Okay, give you. Okay, let's try 0, 1, 1 and 1. 0, 1, we will get 1 here. It will be 0. 1 and 1, we will get 0. Here will be 1. Then this is 0. So means that it is not equal. Law indicate not equal. Okay. In this example, it asks you to design a single comparator that compare X and Y. Determine whether X equal Y or less or more. This one you need to have much more bigger than this, because just now we have only whether it is equal or not. So the solution, you need to come out with the table first. You have here X and Y, right? It doesn't mention about the bits yet. So here you have 0 and 0. Is it equal or not? It is similar. Here will be 1. This one is 0. This one is 0. Yeah, I think so. Let's check it out. Yeah. So here 0 and 1. This one is your mathematical normal. Then from here you can see, you can come up with your own circuit for this output, for this output, and for this output. Let's see, we try one. Which one is easier? Okay, let we pick only this, because this one we already know it is going to use the XO. Now for this part, if it's going to have XY bar, XY bar, we will get like this, X and Y. So we can combine all with another output. Let's find out. Okay, this one is this. Just now I come out with. This one is from whatever we learned just now for a comparator there. And this one, our Boolean expression. So from here we can draw the circuit. Of course, this circuit is very easy if we learn it from our module 4. How to draw circuit from the Boolean equation given. So that is circuits that it asks you to do because you need to design. See, so here you will get x more than y, x equal to y, x less than y. Apply each of the following sets of binary number to the comparator input in the figure and determine the output equality by following the logic level through the circuit. So this one you can try. It is not too high. So you can see here you have 1 0 and 1 0 and 1 0. This one is supposedly similar. Okay. It asks you only to put in the comparator. Just now you know the basic comparator. Okay, like this. This one is for X no. But for this example, didn't ask you to use what, but you can use the XO, which is similar. So you just compare and you get the output. And another one is not similar. You're supposedly going to get a 0. So that is on the comparator. Last previous slide, you see only in terms of circuit, truth table, and boolean. Now you look in the real picture. What is our comparator? Our comparator is under MSI chips 74LS85. So using this chip, we can come out with the comparator things. We should know. Okay, we should know. Okay, we should know all this. All this what? Pin. All this pin input or output. What is this pin number 7? What is this pin number 13? But I think if you need to remember all this might be hard for you, but you need to know how to look. Okay, might be it's going to give you the picture of these MSI chips, and they ask you, okay, what is the pin 7 represent? Okay, if you want to get okay, if you have like 1 0 and 0 1 A and B, what is the value at the pin number 7? Let's say, what is the value at the pin number 5? What is the value at the pin number 3? So you need to know. Let's check here. You can see you have 4-bit comparator. Of course, you're going to have 8 in total, which is 4 for the input A, and another 4 is your 4 input B. So altogether 8 bits for the input, and another not 4 bit, 4 8 8 for the input side, which is including your A and B, and 3 output. You can see here you have A more than B, A equal to B, and A less than B. Please make sure you go through here all what is the functions of your MSI chip 74LS85. Go through one by one, and maybe you can also try to play around with your own input numbers. Okay, determine the A equal to B, A more than B. Input shows. Okay, if you have this, what is the output here? Okay, let me try to check. 0 and 0. We have 0 1 1 0. 0 1 1 0, and another one is 0 0 1 1. Of course, by just looking in these numbers, we know already what we're going to get in our output. It is A more than B, right? So the solution, You're going to compare first. First thing, you're going to compare the first digits of the MSP. Can see, okay, it is equal. So you go for the next. You can see B2 is 0, B1 is 1, which is much higher. So no need for you to compare the rest because you know already, okay, this one is much higher than your B. Stop comparing. See, then you will get 100. What are the comparator output when you have what binary number of k? So what you need to do, you compare this first. It is similar, which is equal. You compare another one, it is equal. You compare another one, it is equal. And lastly, you get the answer. This one is much bigger, then it's going to be the output of A more than B. So you need to have a step by step here. Okay, just now you look into only a single chips. Now you can have the cascade connection with another chips there, and your output will be also becoming your input. So the output of A more than B must be connected to the corresponding input of the next stage there. And for the lower order comparator, A equal to B must be high, where A more than B and A less than B must connected to the low. So you need to know how to connect between each other if you want to have a cascade connection. Okay, this one will be your MSI chips. Your chips number 1. This is your chips number 2. So you just fill in the value there, but you need to know what is the connection. For the chips number 1, A more than B, it needs to connect to the ground. It's asks you to connect to the load there. The lower order comparator, which is this one. Chips number 1 is the lower comparator. Chip 2, 3, 4, 5 is going to connect to each other, but this one is cascade connection only 2. You're going to connect this A more than B, A less than B to the ground. While for A equal B, you need to connect to your source. So you need to remember this statement to come out with this connection. Okay, so next you can see you have decoders. How about decoders? Last time you already learned in your module 1 about the functions of decoder. So this is like a recap also, because you need to learn another things about functions which is similar. Okay, functions of decoder. To detect the presence of a specific, alamak, jatuh pula I punya chocolate. Specific combination of bits or a code on its input. And second one is to indicate the presence of the code by specific output level. So that is the basic functions of your decoder. So decoder has an input line to handle n bits, and from 1 to 2 the power of n. So this one must lebih banyak, which is more than your input. If let's say you have 2-bit inputs, so of course you're going to have like only 2 inputs, right? If you have 2 bits, no, if you have 2 bits, you're going to have 1, 2, 3, 4. Let's say this is A1, A2, B1, B2, and your output will be to the power of n. To the power of 2, you're going to have 4. So you can see here, example type of decoder. If for 3 bits, you're going to have 3 line for the input and 8 line for the output. 1, 2, 3 decoder. 4-bit decoder 1 to 16. Okay, just now this one is a normal or basic decoder might have. This is the maximum number 1 to something, and to the power of 3 equal to 8. You can see here, to the power of 4 you're going to have 16. So that's why you're going to use this formula for your decoder. I guess after this, for decoder, what else? It's going to also apply this one. So I guess you need to remember this one. So there is 3 types of decoder. One is binary decoder. 2 is BCD to decimal decoder, and lastly BCD to 7 segment decoder. Okay, so we're going to look into one by one. Binary decoder first, and then BCD to decimal decoder, and lastly your BCD to 7 segment. For binary decoder, a decoder that recognizes a binary pattern, you're going to have binary input, of course, and it input and active the output whenever the pattern occurs. Use and get if we want the output to be high, and we're going to use NAND. Just add another not there if we want the output to be low. Example, a decoder that produces a high if 1001 occur at the input. Okay, you can try to use this circuit and check the output when you have this input. And you can see over here, okay, this is the things. You have A0, A1, A2, A3. This is your output. For your output to be high. So there is example here. You can determine the logic required to detect the binary code. We have a A4, A3, A2, A1, and A0, and produce an active low. Just now it's already mentioned to you, active low, you're going to use what? Then go back here for active low. This is for our active high. This is our active low. See, we use NAND there. If you have the, when you have 0, 0, your circuit will be having NOT. When you have 0, your circuit will be having NOT. And all the input will be connected to the AND gate. This is very like easy for you. Okay, I give you an example. Let's say you have 1 0 0 1 0, and we want the active low. So this is your input. What is between? You need to know if it is 1, you're going to like having a buffer which is direct, no connection between. If it's not, you need to have 1, everything is 1 here, okay, for the input of your NAND. That's why if it is input directly 1, so here will be also 1. Then for 0, you need the NOT there. 0, you need a NOT to make it as a 1. And here is 1 is directly connect, and here will be having a NOT. That's why after this, if you're going to get a active low because it is a NAND. Okay, second, I hope that you can understand how you're going to develop the logic circuit here by given the binary codes and whether it is active high or active low. When the output is active high, for each decoding gates in the figure, what is the binary code apparent on the input? This one is the twist, vice versa. Just now you were given with the code, binary code, you need to come out with the circuit. Now you were given with the circuit, let's give you a hint. You need to have the value. So here must be 1, active 1, okay, active high. And of course, if this one, you're going to have 1 here, 1 here, 1 here, 1 here also. So this will be direct to be 1, direct to be 1, direct to be 1, and this one will be a 0. And how about this one? This is active high also. This will be a 0, 0, 0, 1. So the value of your example number here 1, 1, 0, and this one 1, 0, 0, 0. Let's take a look into the answer. Very easy for your decoder, isn't it? So now this one is for your binary decoder. So we're going to move to your BCD to decimal decoder. Okay, binary decoder example number 1 is for your bit 3 bits. Later on, we're going to look into 4-bit decoder. Please try to read all of this, and I like to directly give you the overview what is basically happen in your 3-bit decoder. Okay, this is your bits. You have 3 input A, B, and C, and you're going to decode whatever here you're going to decode to using your 3-bit decoder. you have here 0, 0, 1. And your output active high. Active high, you're going to use what? Going to use your AND. Decode the function of A, B, C bar. So here you have 0, 0, 0. For number 1, let's recheck the connection. This will be connect to your node. This will be connect to your node. This will be connect to your node. That's why it is called as A bar, B bar, C bar. So this will be correct. And this will be 1 for this part only. And then for this one, what will happen? You're going to connect A, B, not, and the C will be 1. So you can see here, this C is to be 1. Not connect to the knot. So Q1 is 1. So Q2, what happened here? It's going to be A bar, B, C bar. So this is truth table that you need to remember. You're going to have only specific for the certain output, because you're going to have 8 possibilities. You can see here, 8 possibilities. You're going to have 8 output there. 2 the power of 3 is going to be 8. 3 input, 8 output. You're only going to have 1 output to be active at the certain level or certain input. N is used because we want active high output. If it is active low, we're going to use a NAND. Each input, there will be only 1 high output. This is the things that I mentioned just now. So at this one, which one is the high? At this one, which one is the high? So you need to know that it's only having 1 output at every input value. So the symbol will be, this is the symbol like a block diagram. You have 3 here, you're going to have 8 here, which is 3-bit decoder. Example, if the input is 101, what will happen? 101, it will be at your Q5. And you can see here, this is the value of 5 here. You can see 101. If you change to your from your binary to decimal, you're going to have 5. If you have 001, if you convert binary to decimal, you're going to get 1 here, the rest is 0. So it is like a conversions of your BCD code, binary code there. Sekejap, I pergi ke specific. Mana tadi title? Okay, here. You can see you got the binary number, you want to convert to decimal. So that's why whatever value here is basically represent on your value. 0, Q0, 1, Q1, 2, Q2, 3, Q3. This you call as a BCD number or a code, BCD code, which is binary number basically. You convert to your decimal value. Easy, right? Okay, that's this one 101 4 5. Oh, this one is 5. If, okay, you can see dia tukar. It's twist there. If active high, then you're going to have 1. But for active low, you're going to have a 0 at a specific value. The rest will be high. So you can see this is value of 5. 5 will be 0. The rest will be 1, 1, 1, 1 for your active low. So you need to take note whether either for 3-bit decoder, BCD to decimal, you need to remember it also having the active low and active high. For active high, it's going to be 1 for the output and active low 0 for the output. Now it's basically quite similar. You have 4-bit decoder. So 4-bit decoder, you're going to have 4 to 16. Why 16? To the power of 4 equal to 16. That's why it's going to be 4. You have 4 input there, and your output will be total out of 16. And what is the chips, MSI chips that represent for this decoder? It will be 74HCI54. It's a 1 to 16 decoder. It has active high input and 16 active low output. It also has, okay, slightly different. It's going to have 2 active low, which is enable pin. The pin is used to select the IC if we want to use more than 1 chips. To use the IC, these 2 pin must to connect to the logic low. Low will be a ground. Okay, just now there is no connection to the ground and you don't have EN, but now you have an EN there. It must connect to the logic low. And this is all together 16 output. This all together is our 4 input. How it's look like here. This is example. And to describe the function of each device, there is a lot similar to this table. It's slightly confusing for you, but in terms of numbering, you're going to have low and high, low and high. Okay, let's check. 0, 0, 0. If you still remember, 0, 0, 0 will be a 0. And normally for active high, you're going to have 1 at the specific value of 0. But go back to the hint there. Your input is active high, but for your output is active low. That's why at 0 there, this value is 0. If you convert to decimal, this output active low will be 0. The rest will be 1. Okay, here is our BCD code, which is 001. You convert to decimal, you will get 1. And at the 1 specific, you're going to have active low will be 0. The rest will be 1. So you can do the rest. It's quite easy, right? So this is the things, example for you to check if you have, where is the 000. Okay, this one, I guess, starting from here, you have 0, 0, 0, 0 for the input. Then here will be 0. The rest will be 1. So slightly quite confused, but if you check carefully, high equal to 1, L equal to 0, then you understand, which is similar to this table. So that's why I show you this table first, then you can easily understand. Just now you have here at the high, low things. But you need to know that you need to have low for the input EN enables here. This part you need to connect to the ground, which is the low value. So that's why all of this you're going to have the output. But this condition you can see high, low. Some of it will be having high. So you still cannot have any output, which is all high. Why it high? Because your output should be going to get 0 if it is active input, right? So that is the thing. Please make sure you really carefully understand all of these 3 bits decoder, 4 bits decoder. It is not too hard for you to remember and also understand. Okay, this is example. When you have address decoder, decoder is used a lot to decode an address in a computer. So where you going to apply all these decoder, all these BCD to decimal things. So it's normally used to address, to decode an address of your computer. Let's say your printer there, keyboard, monitor, you have like a keyboard, you instruct anything, you instruct to your controller of your PC, you instruct that you're going to enable or turn on your keyboard, you're going to turn on your monitor, you're going to turn on your modem one by one. So please go through all these functions here. Okay, let's say example, at the port of 0100, input output request low. Okay, this one is input output is low, means that it's correct, then it's turned on. Here will be 0100. You can see the value of this 0100, the value will be 4. So supposedly it's going to turn on your scanner. Salah ke? 10, yeah, here 0100. Then it is 4 there. Value, if you convert to your decimal, then you're going to turn on your scanner. Ting ting. So you can play around with the value there, which one that will be turned on. So BCD, binary code decimal, is a way to express each of the decimal digit with a binary code. There are only 10 code groups in BCD system. The rest will be the invalid. If you still remember, go back and look into your module 2 numbering system. For BCD to decimal, frequently referred as 1 to 10 decoder, the same as binary decoder, expect only 10 decoding gates required. An active low output MSI chip is 74HC42. So this is example. You can see here you have this all pin number, okay, for your pin, sorry. And the decimal digit represent on the input 0, 1, 2, 3, 4, 5, 6, 7, etc. So you're going to have the output value depend on your input value. And you have BDC to 7 segment display. This is your calculator display. You have several display in your calculator. only one display, you need to have these chips. So which one is connected to A, which one is connected to B, C, D, and etc. You can see here. So let's say we have we want to have a 7, okay? What pin that we're going to turn on? We're going to turn on the A, B, and C. A, B, and C. Is it possible to have that? So how to turn on your A, B, C, D for B, C, D to 7 segment? So let's take a look. If you want to display the 7 here, our A, B, and C should be turned on. So you can see here it will be 1 1 1 0 0 0 0 for the output. Supposedly right, because the rest will be 0. You don't want it to be turned on. So you will have the value of 0 1 1 1 for your BCD. Why? Because it is 0 1 2 3 4 5 6 7 7 8 9. All together will be 10. The rest will be invalid. This one is 1. This one is 0. So if 0, we're going to have the output of 0. The output will be 0 like this. It will be. So how the 0 look like? It will be 1 1 1 1 1 1 0. So this display segment output is depending on your display A, B, C, D, E, F, G, but display will be like this. 1 will be 1, 2 will be 2, 3 will be 3, 4 will be 4 in the B, C, D input. The value you change to decimal, you will get 5. The value you change to decimal, you will get 6. The value here you change to this decimal, which is a display 7, 8, and lastly 9. Altogether 10. If you check here, it's mentioned already. Mana ayat dia? Just now it have only 10 decoding for your BCD. This is your numbering system. Okay, in terms of display, you need to know which code. So you put A, B, C, D, and all the input you're going to put the value. So you can play around, try to play in your DIT simulator, I guess so, and look into how it's going to be look like. Okay, let me check how long this video took already. Oh, it's quite long. So I'm going to stop first. Later on, we're going to continue with another video. Continue with our encoder and until lastly the parity generator or code converter. Okay, so have a safe day and bye bye. Meet you again in next video.